Yes, my card would be in my phone right
Does
there.
it still work?
Yes, it works. So it's right there if you need to use it.
Okay.
I'm on stream now though. All right, howdy, and welcome to the review session for exam 1. So, okay. Yes, I'll drop 2 homework grades, and there will be 2 homework assignments due next week. I will post one tomorrow. That'll be due Wednesday, and then I'll post another one Monday that will be due on Friday. Kui Fan asks, can I do homework 2, question 5? Yeah, sure, I can do that. So let's see. This one right here. Okay, so review session. And this is problem 5 from homework 2. Okay, so we have, let me just copy the whole thing because I got a little bit chopped off. Let AX equals B be a linear system whose augmented matrix A bar B has reduced row echelon form, this thing right here. The question A is to find all solutions to the system. And part B is to determine B after you replace the first column here and the third column here with this and this. So let's start with part A. So what I'll do here is I will go back, I'll take my matrix, go over here, enlarge it, and let's look at it. So we have a 1 here, and this is the first one that appears in this row. And then we have a 1 here, and this is the first one to appear in a row. So this and this correspond to bound variables. But this, and this all correspond to free variables. So here is what this means in practice. Let's take our x vector here to have components x0, x1, x2, x3, and x4. Then this line of the augmented matrix corresponds to the fact that x2 plus 2 times x3 plus 4 times x4 is equal to 5. So x2 here is determined as a function by this and this and this. So we can rewrite this as x2 equals 5 minus 2x3 minus 4x4. Where we're basically going to allow x3 and x4 to be anything we want. And likewise, we can take the first line of this matrix, and we can write down the corresponding linear equation, which is x0 plus 2x1 plus 3x3 plus 1 times x4 equals -2. And we can re-express this, or we can express x0 here, the bound variable, in terms of the free variables x1, x3, x4. And if we do that, we get x0 equals -2 minus 2x1 minus 3x3 and then minus x4. So we can express x0 and x2 in terms of the remaining variables. So this gives a complete parameterization of the system. Here's what I mean. The set of solutions to AX equals B is the set of vectors the first component, x naught, will be negative 2 minus 2x1 minus 3x3 minus x4. The second component will just be x1, and then x2 will be 5 minus 2x3 minus 4x4. And then we'll have x3 and x4. And here we're allowing x1, x3, and x4 to be any real numbers we choose. So this completes part A of the problem, and it gives a complete description of solutions to this linear system. Now part B is a little bit more tricky. Okay, lots of questions. Let me finish this problem, and then I'll go through all these questions. So let's look at part B here. And so here's how we deal with part B. What we're going to do is we are going to take A1 here and A2 here. And we are going to replace them in this matrix. So we're also going to take the set of solutions we have right here. And we're going to want both of those handy. So what we're doing is, because this is A1 and this is A3, we're going to replace the first column here with this, and the third column here with this. So our new matrix is going to be the matrix 1, 0, 0, and then 2, 0, or sorry, I'm being an idiot. Our first column is going to be 1, 1, 3, 4. Our second column is going to be 2, 0, 0, 0. Our third column is going to be this thing. So 2, negative 1, 1, 3. And then our fourth column is going to be 3, 2, 0, 0. And our fourth column is going to be 1, 4, 0, 0. Now what we're doing is we're using the solutions we found here, and we're inputting them to our new matrix. So what we're doing is we're feeding this negative 2 minus 2x1 minus 3x3 minus x4, x1, x3, or I'm sorry, I missed x2. So 5 minus 2x3 minus 4x4, and then x3, and then x4. And so we're going to multiply this matrix by this vector. And this is a long, tedious computation. So here we're going to have negative 2 minus 2x1 minus 3x3 minus x4. And in fact, just to kind of make my life easy, I'm going to copy paste this a few times. So I'll put that here, I'll put that here, I'll put that here, and here it's going to be next to a 1, a 1, a 3, and a 4, and then it's going to be plus 2x1, and then plus 2 times 5 minus 2x3 minus 4x4, and then plus 3x3 plus 4x4. Oh wait, 3x3 plus 1x4. So now let's continue on. Here we'll have minus times this thing. So put that down here. And then plus 2x3. And then plus 4x4. And then down here, we're going to have just plus this times 1. And then finally, we're going to have plus 3 times this. And I'll leave it to you to do any simplifications because all the terms here can be collected. But this gives an expression for the new b, and the new b is actually a function of the variables x1, x3, x4. So basically what they're asking you to do here is alter this matrix and then see how the set of solutions changes. Okay, so let's go through the other questions that people are asking. So I'll start back here, even though I already answered that. Daniel Casano asked, do I plan on dropping 2 homework grades? And yes, I will. Can we go over exam information, such as calculator or not? What service we'll be using? We'll be using Zoom. So let me put that in Discord as well. And you will be allowed to use a calculator. I think I said that at one point before, but I'll say it again. Hand calculators will be allowed in the exam, but you can't use anything like Wolfram Alpha that requires your PC /phone. Brian Chong asks, after this question, can you go over and underdetermined systems and how they can have infinite and unique solutions? All right, I'll do that, and then I'll do Savannah's question. So, over and underdetermined systems. I'll start with overdetermined systems. So here's what we're going to do is we're going to assume n, let's assume here that n is greater than m. And we're going to look at an m by n matrix. So here we'll have alpha 1, 1, alpha 2, 1, alpha 1, 2, blah, 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 all the way over until alpha 1n, and all the way down until alpha m1, and all the way over until we get to alpha mn. And an overdetermined linear system is something like this matrix multiplied by a vector like this. And being set equal to a vector like this. So here's the key feature of the system. There are more variables than equations. And as soon as the system excuse me, has one solution, it has infinitely many. So here's roughly why this is true. If this was the matrix A, and this was the vector of variables x, and we were setting it ax is equal to c, then a natural way to solve this, at least one that is related to what we were doing in lectures, was take this matrix A and attempt to put it in row-reduced echelon form. And you can do that essentially by performing a sequence of row operations. Now, after putting our matrix in row-reduced echelon form, it has to look something like this. You have a 1. Okay, maybe you have a 1 here. How about I do something a little generic? And you have zeros, then you have a 1, and then you have something like, you know, alpha, dot, 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 beta, and then below that, you have 0, 0, 0, 0, 0, and then here you have maybe another 1. And then, you know, you might have sigma, dot, 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 gamma, and so on. And these ones right here correspond to bound variables. But because our matrix is m by n, where m is less than n, there are always less bound variables than free variables. So the moment you're able to obtain a single solution to a system like this, a single non-trivial solution, you in fact get infinitely many. And one way to kind of phrase this in terms of the language that we developed this last week is if we're looking at the system ax equals c, we can also look at the system ay is equal to 0. And the set of solutions of this is the null space n of a. And if we're looking over here at ax equals c and x naught is one solution, then a x naught plus y for y in the null space is another solution. And so roughly what happens is that the dimension, I'll put it in single quotes, of the space of solutions ax equals c, if a solution exists, is the dimension of the null subspace. All right, so that's what I have to say on overdetermined systems. Let me talk about under. Oh wait, I'm sorry, I'm being an idiot. Everything I just said was correct, but I was saying it for underdetermined systems, not overdetermined systems. Sorry, I get a little dyslexic sometimes. Underdetermined systems is when you have more variables than equations. And overdetermined systems are the other ones. So for an overdetermined system, you have n is less than m, but you have the same general setup. So I can just actually copy paste this and go over here. And the key difference now is that there are more equations than unknowns. And generally, such a system will not have any solutions. And I say generally because this is not always true. To give an example, we could look at something like this. 1, 1, 1, 1, 1, 1. So this would be a 3 by 2 matrix. And we could multiply it by the column vector of size 2, x1 times x2. And we could set it equal to 3, 3, 3. So this is an overdetermined system. But even though it's overdetermined, it still has a solution because I can, for example, just take x1, x2 to be equal to like maybe 1 and 2, or I could have also done 2 and 1. Many such combinations work. So even though this is an overdetermined system, it still has solutions. But generally speaking, if I had something like this, 1, 1, 1, 2, 1, 3, and I was multiplying this by, say, x0 or x1, x2, and I was setting it equal to 1, 1, 1, well, actually no, this would have a solution. But if I change it slightly, put a 2 here, you guys can check that by trying to put this matrix together with this vector in a single augmented form in doing row reduction, you can check that there's no solutions to this. And this in fact illustrates what happens very generally with overdetermined systems. Okay. So Savannah asks, can we go through number 7 on this homework as well? So I assume this is homework 2. So let's do number 7. This is a fun problem. Okay, so let A be an n by n matrix, and we're assuming here that A squared is the 0 matrix. Then the claim is that I minus A is non-singular, and I minus A's inverse is I plus A. So let's see why this is true. Suppose we take I minus A, and remember here that I is the identity matrix. And we multiply it through by I plus A. Well, matrix multiplication is distributive. So this is going to be the same thing as I squared, and then minus A times I, and then plus a times I, and then minus a squared. Well, I'm going to use a bunch of facts here. One fact is that if you multiply the identity matrix by the identity matrix, this is the same as I squared, and it's actually just equal to the identity matrix. So this just becomes I. If you multiply any matrix by the identity matrix, you get your matrix back. And it doesn't depend whether you multiply on the left or the right. So this right here becomes minus A. This right here becomes plus A. And finally, we're going to use the fact given here that A squared is the zero matrix. So this is the same thing as minus the zero matrix. This will cancel with this. And so I'll be left with I minus the zero matrix. But if you subtract the zero matrix from anything, you just get the same matrix back. So this shows that when you take I plus A and you multiply it by I minus A, you get the identity matrix, which means I plus A is the inverse of I minus A. And that implies two things. It implies that I minus A is non-singular. And directly from definition, it also implies that its inverse is I plus A. And so that completes the proof of this homework problem. Connor asks, what led me to multiply I minus A with I plus A? Well, what did that is, let's look at the problem. The problem itself is telling us that we need to check that I minus A's inverse is I plus A. So to check if one matrix is inverse to another, the natural thing to do is multiply them and see if you get the identity matrix. Well, we have to know proofs for the test. You won't have to know any of the proofs I proved in class, although you should have a conceptual understanding of why they work. A lot of the proofs that I would give would be more proofs that are computational. How should I say this? I don't want you to prove things exactly the way I proved them in class. I kind of want you to understand the computational techniques underlying the proof and be capable of executing those yourself. So often what is more relevant than the proofs in lecture are, the homework problems or the examples I do in class. As for how many questions are on the test, seven questions. I don't know if there's examples on the homework you can review for over underdetermined systems. I can check. let's see. I mean, technically, yes, there are. Like, C here is an example of an overdetermined system, whereas A here is, you know, or B here is an underdetermined system. But they're not sketched out exactly. So let's say we look at this. I talked about them in my lecture, but another place you could learn about them is if you go up here and you look at, let's see, yeah, here. So page 31 of the textbook, they talk about underdetermined systems. They give several examples. And they go through the process that you do to study them, which is essentially just row reduction and putting your matrix in row-reduced echelon form. And likewise, you can approach overdetermined systems in the exact same way. You take your system and you apply row reduction, and then you kind of try to see if you can solve it using back substitution. Please use Zoom through your computer. And I hope you guys all have a webcam. If you don't and you have to use it through your phone, that'll be okay. It's just for these summer courses, we've kind of been struggling to find good ways to proctor. What we like to do is we like to kind of have complete vision of what you guys are doing, and a webcam is one way to do that. Kyle asked, can I go over a back substitution question? Yes, I can. And Ultimate Calculator asked, is span just a grouping of vectors or is it something else? Savannah asks, will we be able to print out the test after it's released to look at it, or will we have to? You can print it out, but that will take time out of the time you have to do other things, so you'd want to print it out quickly. Okay, now we have several. Okay, Mark asks, my laptop has been acting up lately. Yeah, you can use your phone. Again, I'd prefer you use your laptop if you have a webcam available, but if you don't, I'll accept a phone. Okay. So now that we've answered those questions, let's talk about the math questions that we got asked, and I'll go in order. Can we go over a back substitution question? So let's go back to homework 1. How about we look at E here, and we try to solve this with back substitution. So I'll take this, and then I'll go over here. So this is from homework 1, and the associated question is to solve the linear system. The first thing I'm going to do is I'm going to convert this into augmented matrix form. And if I convert it into augmented matrix form, I'll have 2, 3, 1 here, 1, 1, 1 here, 3, 4, 2 here, and then 1, 3, 4 here. Now, we want to solve this system using row operations. First thing I'm going to do is I'm going to swap row 1 and row 2. I'll do a swap. If I do a swap, I'll have 1, 1, 1, 3, 2, 3, 1, 1, and then 3, 4, 2, 1. or 4. And the next thing I'll do is I will do my row operations to cancel out the 2 and the 3 here. So I'll set row 2 equal to row 2 minus 2 times row 1. I'll set row 3 here equal to row 3 minus 3 times row 1. If I do that, the first row doesn't change. The second row becomes 0, 1, and then -1. And then I'm subtracting 2 times 3 from 1, so I'll have -5 here. And this will be a 0. This will be a 1. And this will be a -1. And now I'm subtracting 3 times 3 from 4. So I will also get -5 here. Now what I can do is I can subtract row 2 from row 3. If I do that, I have 1, 1, 1, 3, 0, 1, -1, -5, 0, 0, 0, 0. And then what I can do is I can, to put this in row reduced echelon form for real, I have to get rid of this 1 because it's kind of above a pivotal 1. So I'm going to set row 1 to be equal to row 1 minus row 2. If I do that, I'm going to have 1, 0, 2, 0, 1, -1, 0, 0, 0. This will stay -5, this will stay 0. And I'm subtracting this from this, so I'm adding 5 to 3, so I get 8 here. Now, this right here is in row reduced echelon form. And now I can go about solving this system. So I'll take this, and I'll bring it over here to study it. If my vector of variables is x1, x2, x3, this corresponds to the equations x1 plus 2x3 is equal to 8, and x2 minus x3 is equal to -5. Here we see we have a 1 here and we have a 1 here. So this one and this one correspond to bound variables. So this right here and this right here are both bound variables. And this right here is a free variable, because you never get a pivotal 1 in the column corresponding to it. So now we can go about the back substitution process. First thing we do is we try to solve for the bound variables in terms of the free variables. So we set x2 to be equal to -5 minus x3, or plus x3. And then we could use this to back substitute in here, but because there's no x2, we don't really have to do anything. So we would get x1 is equal to 8 minus 2x3. Okay, so this is not the best example in the world, because the way it worked out for us in the end is that we didn't actually have to do back substitution. Let me choose a better example. Maybe I'll do one of the 2x2s, this way I can do it quickly. this here would be 2, negative 3. I'm going to alter this a little bit to make it more interesting for us, and I'm going to replace this with a 5. So this will be negative 4, this will be 5, and it's going to be multiplied by x1, x2. It's going to be equal to the vector 5, 8. So we'll go through the same process and study the augmented matrix 2, negative 3, negative 4, 5, 5, 8. First thing I'll do is I will add 2 times row 1 to row 2. If I do that, I'll have 2, negative 3, 5. And then I will have negative 1 here and 18 here. All right, now I can go about solving this. I don't have to even go all the way to row reduced echelon form. So I would get negative x2 is equal to 18, which is the same as x2 being equal to 18. So I'm starting from the bottom here. And then the next equation up would tell me that 2 times x1 minus 3 times x2 is equal to 5. Now I can actually do a back substitution, and I can take what I know about x2, and I can plug it in for the x2 here, and I get 2x1 minus 3 times 18 is equal to 5, which means x1 is going to be equal to 5 plus 3 times 18 divided by 2. So you can see the general process in this simple example. You start by solving for x2, and then you use what you know about x2 to solve for x1. Connor says, wouldn't it be x2 is equal to negative 18? Did I mess that up? Oh, yes, I did. Thank you. So here I should have a negative 18 here, and then I should have a negative 18 here. Okay. So this completes a back substitution example. Let's go up to the next math question. Is span just a grouping of vectors, or is it something else? So I'm going to give you guys the actual definition of span. So I want to emphasize that this will not be on the exam tomorrow. The stuff we're doing from chapter 3 right now will show up along with the stuff we do in chapter 4 on exam 2, not exam 1. But since someone asked, and this is a relatively easy thing to explain real quick, I'm just going to do it. Span of V1 through Vn is the set of all combinations like this. So this and this. So it's a very, very large set generally, but the good thing about it is that span of V1 through Vn usually turns out and in fact, I shouldn't say usually, I should say always. Always turns out to be a vector space. And not only is it a vector space, but in fact, a subspace of V. So span of V1 through Vn is kind of a way to generate a subspace of your vector space. by looking at all linear combinations of your vectors. Okay. Connor asks, what does it mean for a matrix to be singular versus non-singular again? Okay, so let A be an n by n matrix. Then A is non-singular. If there exists a matrix B with A times B is equal to B times A is equal to the identity matrix. In such cases, we say A is invertible and write A inverse is defined to be B. So one of the important things about a B matrix being non-singular is that if A is non-singular, then the determinant of A is not equal to 0. In fact, if the determinant of A is not equal to 0, then the matrix is non-singular. So the determinant non-vanishing is equivalent to the existence of an inverse matrix. Furthermore, if A is non-singular, then AX equals B has a unique solution for any B. So all three of these ideas are related. Sometimes if you want to show a matrix is non-singular, you can do it by exhibiting an inverse matrix. The inverse matrix can be computed basically by Gauss-Jordan reduction. Or what you can do is you can check that the determinant doesn't vanish. And if you know either of these things, then you also learn this final thing, which is that if A is non-singular, then the system AX equals B has a unique solution for any B, which is a very useful theoretical fact. Benjamin asks, do we need to memorize the row operation rules? I would say yes. It's very, very useful to memorize them. You need to know how to perform row reduction. You need to know how to put a matrix in row reduced echelon form. And you need to be able to recognize the utility of row reduced echelon form. You also need to understand how you can use row reduction to compute inverse matrices. Okay. What was the last lecture that will be on the exam? T-Row 55 asks. Yeah, Kramer's rule is one of the last concepts that will appear on the exam. How will we be submitting our answers? Harrison asks. You may write your answers on paper. Like get some notebook paper, write down your exam answers on it, and then scan those exam answers. Ideally, if you have a scanner. If you don't have a scanner, you can use a very bright light, and you can take very clear pictures of your exam answers, get them all in a bunch of pictures, and put them inside of a PDF. And it's very important that you do that because if you don't put them inside of a PDF and you just send me images, I won't have a good way to give you guys feedback on what you got wrong on the exam. The disadvantage of grading through eCampus is that it only lets me and the graders do annotations if the thing you submitted is a PDF. Connor asks, can we go over a Kramer's rule example? Sure. So let's get Kramer's rule handy. I think I have it somewhere in here. Do I not? Okay, maybe I don't have Kramer's rule in here. In which case, let me just grab it from the textbook so we can all look at it. Alright, so this is Kramer's rule. Let's apply it to a concrete problem. And how about I do the problem that we had before? Simply because we already solved it one way, so when we solve it this way, we'll know if we have the right answer or not very quickly. So Kramer's rule gives us a technique for solving a linear system like this using determinants. So in order to do this, what you have to do is you have to take your matrix, in this case A, and you have to produce different matrices AI for I equals 1 to n. In this case, we only have two i's to worry about. So we have here I equals 1, and we have I equals 2. In this case, the A1 is going to be the matrix obtained by taking A and replacing the first column with 5, 8. So A1 here is going to be 5, 8 in the first column, and negative 3, 5 in the second. And the determinant of A1 is going to be equal to 25 plus 24, which will be 49. For A2, what I do is I take the matrix A, I replace the second column with 5, 8. So I have 2, negative 4 here, 5, 8 here. And I take its determinant. And this will give me 16 plus 20, which will give me 36. And now the last thing I need is I need the determinant of A itself. So I need to look at the determinant of 2, negative 3, negative 4, and 5. And so this will give me 10, and then minus 12, so negative 2. And now I have all the information necessary to apply Kramer's rule because it tells me that x1 here is going to be equal to 49 divided by -2, and it tells me that x2 here is going to be equal to 36 divided by -2, which is the same as -18. Now, you'll notice that the -18 here we got for x2 was the same as the -18 we got here when we solved this via back substitution. And you can also check that 5 plus 3 times 18 is, wait a second, 5 plus negative, oh, no, okay, it does work out to be correct. So this answer, x1, agrees with this answer, x1 here as well. This is how we can use Cramer's rule to solve linear systems, ax equals b. Yeah, the exam probably will be posted about 5 minutes early. All right, do people have more questions? All right, well, I am gonna, a volume example, okay. I'm gonna go take a 4-minute break and just grab some water, and then I'll come back and I will do more examples. I'll do a volume examples and a 3x3 Cramer's rule, and whatever else you guys want. All right, I'm back. Let me do a volume example. So I'm going to look at parallel pipettes, and we're going to look at, say, this. So I'll just make up a problem. Find the volume of the parallel pipette spanned by, let's say V1 here is going to be 1, 4, 2. V2 here will be 3, 6, 8. Actually, I'm gonna make my life a little easier. I'll do 1 here. And then V3 here will be 1, or maybe I'll go 2, 10, and 5. So I'm going to stipulate that I want the absolute volume. And so by the absolute volume, what I mean is not the oriented volume, but the absolute value of the oriented volume. So in order to compute this volume, what I'm going to do is I'm going to take these 3 vectors and I'm going to arrange them into a matrix. My matrix here will be A. It'll be 1, 5, 2, 1, 6, 8, and 2, 10, 5. Now I could either compute the determinant of this via cofactor expansion, or I could compute it using row reduction. I'm going to do both just to give you guys a little bit of insight. So one way to compute the determinant of A is via cofactor expansion. So I'm going to cofactor expand along the first row, which will be 1 times the cofactor 6, 10, 8, 5, minus 5, 2, 10, 5, and then plus 2, the cofactor 5, 6, 2, 8. So here I'm going to have, so this is 5 times 6, so 30 minus 80, so negative 50 here. And then minus 5 times 5, so it's 25, minus 20, so minus 5. And then plus 2 times, let's see, 5 times 8 is 40, minus 12 is 28, so plus 2 times 28. And so if we simplify this, I think we just get 1. Am I right? Or am I being an idiot? Negative 50. Okay, it is 1. All right. Sorry, my brain is not working very well right now. But so we find that the determinant of A is 1, and that's also, I mean, it's positive, so I don't have to take any absolute values. So we have computed this using cofactor expansion. Let's try to compute it another way that essentially involves row reduction. So what I'm going to do is I'm going to set row 2 to be equal to row 2 minus 5 times row 1, and set row 3 to be equal to row 3 minus 2 times row 1. And if I do that, I'm going to get 1, 0, 0 here, 1, 1, 2 here, 1 here, 0 here, and then 6 here, and then negative 4, or no, just 1 here. Okay, and next thing I do is I take row 2 and I subtract 6 times it from row 3. So row 3 is going to be equal to row 3 minus 6 times row 2. And that gives me the matrix 1, 1, 2, 0, 1, 0, 0, 0, 1. And if I look at this matrix right here, this is upper triangular. Note that I've only applied type 3 row operations. So that means that the determinant of this is going to be the same as the determinant of this, but because this is upper triangular, I can just read off its determinant by taking the product of the values on the diagonal. So the determinant here is equal to 1. So this gives two different computations of the absolute volume of the parallel pipe bed. Okay, let's see what else people want me to do. A Kramer's rule for a 3x3. Okay. I'm going to do the following linear system. So here I'll have 1, 1, 3, and then 4, 5, 2, and then 3, 0, 7. That'll be my matrix, and I'm multiplying it by x1, x2, x3, and I want it to be equal to 1, 5, 6. Maybe I'll make my life even a little bit easier, and I'll just choose easier coefficients, so 1, 2, 1. So this is my linear system, ax equals b. If I wanted to, I could solve it using Gauss-Jordan reduction, but right now I'm going to try to solve it using Kramer's rule. So first thing I'm going to do is I'm going to compute the determinant of A. I'll do this via a cofactor expansion. So 1 times the determinant of this minus 1 times the determinant of this, and then plus 3 times the determinant of this. And so right here I get 35. Right here I get so minus 28 minus 6, and then plus 3 times negative 15. So 35 minus 22 minus 45. So I believe this is the same thing as negative 32. And if you guys see any error with this calculation, let me know. Okay, so I'm going to trust that I have the right calculation here. And now I'm going to go on to the remainder of the Kramer's rule calculations, and they take a little bit. So first thing I'm going to do is I'm going to solve for x1, and I can do that by writing down the matrix A1, which is the matrix A, except you take the first column and you replace it by the vector B. So I'll have 1, 2, 1, 1, 5, 0, and then 3, 2, 7. And what I need to do is I need to compute the determinant of A1. So if I want to do that, I'll have 1 times 5, 7, 0, 2, and then minus 2, 7, 1, 2, and then plus 3, 2, 0, 1, 5. So I'll have here minus 15. I'll have here minus 12, I believe, because 2 times 7 is 14, minus 2 times 1. And then here I'll have 35. So if I subtract 15 from 35, I get 20. If I subtract 12 from that, I get 8. So I get 8 here. So this is going to be 8 divided by negative 32. So this solves for x1, and it remains to solve for x2 and x3. So now let's try to solve for x2. In this case, the matrix A2 here is going to be the matrix 1, 4, 3, 1, 2, 1, 3, 2, 7. And the determinant of A2 is going to be 1 times 2, 7, 1, 2 minus 1 times 4, 7, 2, 3 plus 3 times 4, 1, 2, 3. So we have to do this computation. This right here is just 12. This right here, 4 times 7 is 28. Minus 6 is 22. So we'll have minus 22. And then plus 3 times negative 2. So I'm going to have 12 minus 28, which will be the same thing as negative 16. So x2 here is going to be negative 16 divided by negative 32, which is the same as 1/2. Okay. Next thing we have to do is we have to compute x3. For x3, we have to write down the matrix A3. And so this one is going to be 1, 4, 3, and then 1, 5, 0, and then 1, 2, 1. And we have to compute its determinant. And the determinant of A3 is going to be this cofactor minus this corresponding to this subblock, and then plus 1 times this cofactor. So we do this calculation. This right here is 5. This right here is minus 2. And this will be plus negative 15. So negative 15 and 5 is negative 10. So this is just going to be negative 12. So I'm going to put negative 12 here, divided by negative 32. Okay, so this completes the computation of x1, x2, and x3. And that's how we apply Cramer's rule to a 3x3. Kyle asks, how do you know when to use a row or a column to find determinant of A? The answer is that you can use any row or any column. It doesn't matter, you just have to pay careful attention to the signs. Savannah asks, I still don't understand the volume example. Can we go over how the determinant is the volume? Okay. I don't really know a good way to explain this. It's just kind of one of those facts you have to remember, but I can motivate it based on something you've seen before. So let's recall, and this is a fact you might learn in multivariable calculus, that the determinant, or that the volume of a parallel pipette spanned by A, B, and C is A dotted with B cross C. So this concretely is the same as A1, the first component of the vector A, multiplied through by B, so what is it? So I believe this will be B2, C3, minus B3, C2, and then minus A2, and then here it will be B1, C3, minus B3, C1, and then plus A3 times B1, C2, minus B2, C1. Well, this is a fact you learn in multivariable calculus. But this is really the same thing as A1 times the determinant of this. So this would be B2, B3, C2, C3, and I'm taking the determinant, minus A2 times the determinant of B1, B3, C1, C3, plus A3 times the determinant of B1, B2, C1, C2. And you can then recognize this as the cofactor expression of the determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3. And this is the same because the determinant of a matrix is the same as the determinant of its transpose, as the determinant of A1, A2, A3, B1, B2, B3, and C1, C2, C3. So this calculation explains why the computation of this is the same as the computation of this. And this is the way you learn how to compute the volume of a parallel pipette in multivariable calculus. Okay. Any more questions? Oh, Mark Link asks, what's the difference between absolute volume and oriented in terms of computations? For oriented volume, the ordering of the vectors matters. So I'll do a very, very simple example of this. Oriented volume of parallel pipette spanned by E1, E2, where these are the standard basis vectors, is the determinant of the matrix 1, 0, 0, 1, which is just 1. On the other hand, the oriented volume of the parallel pipette spanned by E2, E1, where I've changed the order, is the determinant of 0, 1, 1, 0, which is negative 1. So by switching the ordering of these two vectors, I have switched the oriented volume by sign. However, both of these parallel pipettes have the same absolute volume. So if you take the absolute value of this, you get 1, and if you take the absolute value of this, you get 1. A Gauss-Jordan problem, okay. So let me take one from the homework. How about we do B here? So what we want to do is we want to use Gauss-Jordan reduction to solve this matrix. So here we have 1, 3, 1, 1, 2, negative 2, 1, 2, 3, 1, 2, negative 1, augment 3, 8, negative 1. Now I'm going to apply a sequence of row operations to put this matrix right here in row reduced echelon form. So first thing I'll do is I will set row 2 to be equal to row 2 minus 2 times row 1. And the reason I'm doing this is I want to use this 1 right here to get rid of this 2 right here. And I'll also set row 3 to be equal to row 3 minus 3 times row 1. And if I do that, I will use this 1 right here to cancel out this 3 right here. So I get 1, 0, 0 here, 3, 1, 1, 3 here, and now I have to figure all these other entries. So if I subtract 2 times 3 from 2, I'm going to get negative 8 here. If I subtract 3 times 3 from 1, I'm going to get negative 8 here. If I subtract 2 times 1 from here, I'm going to get negative 1 here. If I subtract 3 times 1 from here, I'm going to get negative 1 here. If I subtract 2 times from 1 from here, I'm going to get 0. And if I subtract, hold on, if I subtract 3 times 1 from here, I'm going to get negative 4. If I subtract 2 times 3 from 8, I'm going to get 2. And if I subtract 3 times 3 from negative 1, I'm going to get negative 10. Let's see, did you guys all agree with all my computations here? Do I agree with all my computations here? Okay, I agree with myself, which is good. I like agreeing with myself. So, we have this matrix. Next thing we're going to do is we're going to subtract row 2 from row 1, or from row 3. So we'll set row 3 here to be equal to row 3 minus row 2. If we do that, the first row remains unchanged. So we have 1, 3, 1, 1, augment 3, 0, negative 8, negative 1, 0, 2. And then here we'll have a negative 12. We'll have 0, 0, 0, negative 4. Okay, so now we want to do the last steps. This is not in row reduced echelon form, but it's it's getting there. It is in echelon form, just not row reduced echelon form. So what we have to do is we have to do some queening. So the things I'm going to do is I'm going to set row 3 to be equal to, I'm going to divide all of row 3 by -4. And I'm going to divide all of row 2 using the row scaling and dividing by -8. And if I do that, I'm going to have 1, 3, 1, 1, 3. And then here I'll have -1/4. And here I'll have 3. I'll have a 1 here, a 0, 0, 0 here, a 0 here, a 0, no. A 0 here, a 1 here. Sorry, actually that's incorrect. This should be a 1. This should be a 1/8. And this should be a 0. Do I agree with all that? This looks right. Now I can put things in row reduced echelon form. Almost. So I'm going to set row 1 to be equal to row 1 minus row 3. If I do that, I'm going to have 1, 3, 1, 0, augment 0, 0, 1, 1/8, 0, -1/4, 0, 0, 0, 1, 3. So now we go up here and we take row 2 and we subtract 3 times it from row 1. So we set row 1 equal to row 1 minus 3 times row 2. And this becomes 1, 0, and then 1 minus 3/8. And if I do that, then this is actually the same thing as 5/8. And then 0. And then 3/4. And then 0, 1, 1/8. 0, -1/4. 0, 0, 0, 1, 3. And alas, we have something in row reduced echelon form. So let's see what this tells us. The bottom row here tells us that x4 is equal to 3. And then we have to have x2 is equal to -1/4 minus 1/8 times x3, or x3. And then finally, this one right here, the first row, tells us that x1 has to be equal to 3/4 minus 5/8 times x3. So this gives us all the data we need to write down the set of solutions. So we'll take it over here. the set of solutions to the system is we have a 3 here for our x4. x3 is allowed to be anything. x2 is negative 1/4 minus 1/8 times x3. And x1 is 3/4 minus 5/8 times x3. And x3 can be any real number. And so that solves our linear system. Okay. Okay, so this completes the Gauss-Jordan example. Does anyone have any more questions? Any proofs I ask of you would be very basic proofs. The closest example to like a proof-like thing that I might ask would be something like, let's go back up here. So one of the first questions we dealt with today was this one. Let A be an n by n matrix. Show that if A squared is the zero matrix, then I minus A is non-singular, and I minus A inverse is I plus A. And so, this just amounts to doing it, proving this amounts to doing a computation, basically. And you have to kind of know the axioms that you're using. Like, for example, here I was taking advantage of the fact that A times the identity matrix is A, regardless of which side I multiply the identity matrix on. As well as the fact that if you multiply like the identity matrix by anything, you just get, the identity matrix. So I squared is equal to I. The point of this is to kind of outline what would be expected when I ask you to prove something. I'm not asking you to do a formal proof like the ones I've been doing for the vector space stuff. I'm asking you to kind of be able to do an argument like this, which is kind of a computation, but it's a computation that involves recognizing the role that different things are playing and how all the different kind of axioms enter into the computation. So there will be no formula sheet or cheat sheet. The expectation is that you know how to do the main computations. There really aren't that many formulas for a course like this. I guess the one formula that if I was a student I would feel like I would need to memorize is the determinantal formula. And if I had to kind of encourage you guys to spend time like just trying to memorize anything, it would be, effectively memorizing this, basically. Where is it? Here. And this is just the fact that the determinant can be expressed as a cofactor expansion in terms of these cofactors, aij's. And the key thing to remember, and this is the thing that everyone always forgets when they're computing determinants, is that when you're computing these cofactors, the cofactor can have a different sign depending on where it is in the matrix, and the dependence of the sign is this I plus j term here. So that's something a lot of people often overlook when they're doing these computations. Okay. So any final questions before I wrap up for tonight? All right, well, good luck on the exam tomorrow. If you guys need to ask anything between now and then, the one thing you guys can use in Discord that no one has really used that much is the help channel. I'll be up for several hours more tonight, and I can kind of answer questions on and off as people ask them. And for the exam, try to get there about 10 minutes early, just in case you need to check to make sure Zoom is working on your device. And also to kind of download the exam, print it out, and get it on a piece of paper if you want it on a piece of paper. Either way, it always requires a bit of preparation time. And other than that, I wish you guys good luck on the exam tomorrow. I finally got yesterday's lecture posted on YouTube. It took forever to process. So at some point, between now and Sunday, please watch this. Because it has some very important stuff that's going to be important in Monday's lecture. I'll also have some homework posted at some point between now and tomorrow that will be due next week, I believe Wednesday and Friday. So anyways, that is all for now, and good luck tomorrow again. Kyle asked, will there be a curve if scores are bad? I like to look on the bright side and hope they're not bad. But if they are, then, sometimes curves are necessary. But I can't commit to anything before the exam. So, good night for real this time, and good luck tomorrow.